Howdy. In this example, we're going to practice calculating contact stresses. As you can see in the figure, we have a hardened steel alloy ball that is seated on a hard bronze alloy seat. And what we're going to do today is we're going to calculate the maximum contact stress, the contact area, and the maximum value of the subsurface shear stress. To do that, we're going to rely on the Hertz contact stress equations. The first one over here is going to give us the contact pressure or the contact stress. If we take a look at it, we see that it depends on F, which is the force between the two components, R1 and R2, which are going to be the radius of the spherical ball and of the seat, and the parameter delta over here. The second equation A is going to give us the radius of the contact area. It also depends on the force, delta, and the radiuses. Right, so let's go ahead and begin by writing down all the unknowns that we have. Now the order of the components doesn't matter. And what I mean by that is it doesn't matter which one you pick for R1 or R2, as long as you keep all of those consistent. So in this example, we're going to go ahead and call this one our component number 1, and the bronze seat the component number 2. Now remember, we're going to need the radiuses, the Young's modulus, and the Poisson's ratio. So in regards with the steel ball, right, what is going to be our radius? Let's put it over here. From this figure, they give us the diameter, but we need to use the radius. The radius is nothing but the diameter by 2. So in this case, it's going to be 6 millimeters. Now the problem statement doesn't give us any material properties for the steel alloy or the hot bronze, but we can quickly figure those out by looking them up into material properties tables. If we look at our machine elements handy booklet, we'd see that the hardened steel alloy is going to have an elastic modulus, we call it E1, of 207 gigapascals. And the Poisson's ratio is going to be 0.3. Now let's write the parameters for the hard bronze alloy. Let's start with the radius. We'll call it radius 2. Here we give us a diameter 12.2, so half of that is going to be 6.1 millimeters. The elastic modulus from the table is going to be 110 gigapascals. And the Poisson's ratio is going to be 0.33. So with this information, now we can go ahead and calculate the parameter delta, because we're going to use this value for both the contact pressure or stress and the radius equation. So let's start by calculating the value of delta. So delta is going to be 1 minus 0.3 squared divided by 207 gigapascals. Now, I like to work these problems in units of megapascals because I want to calculate a value of stress, right? And stress is usually given in megapascals. So if this is 207 giga, right, this is going to make it 207,000 megapascals. So to that, we're going to add 1 minus the Poisson's ratio of the bronze alloy, which is 0.33 squared, and then divided by the elastic modulus, 110, and I'm going to type 110,000. So if we type this on the calculator, 1 minus 0.3 squared divided by 207,000 plus 1 minus 0.33 squared divided by 110,000. This gives a value of 1.2497, and I'm going to keep that extra decimals. This is times 10 to the minus 5. And let's look at the units, right? Poisson ratio is unitless. At the bottom we have megapascal, so this is 1 over megapascal. So with the value of delta already calculated, we can go ahead and use this equation over here to calculate the contact stress. So contact stress is equal 0.578 times the force, 1,500 newtons, and then times 1 divided by radius 1. So radius 1 is 6 millimeters, plus 1 divided by radius 2. Which was said was 6.1. However, right, well, the magnitude is 6.1. Remember that when we're dealing with the contact stresses, right, if you have a sphere, this radius is going to be positive. If you have a plate, then we use infinite radius. And if you have a concave or like a socket, like in this case, then that radius has to be negative. So yes, it's 6.1, but it has to be negative, right? So we're not adding these two quantities together. At the end of the day, we're subtracting. Now, this quantity gets squared. And remember, we have newtons. At the bottom, we have millimeter, and this is squared. So Newton per millimeter squared, this is a megapascal. And then this megapascal, at the bottom, we have the value of delta, 2.497 times 10 to the minus 5, 1 over megapascal. And this value gets squared, right? So this megapascal in the denominator of the denominator of this fraction, right, is going to get squared times 1 megapascal. Over here is going to have megapascals to the power of 3. And then we're going to get the cube root. So if we plug all of these values into the calculator, just as they are over here, whatever comes out is going to have units of megapascals. So we go ahead and type this. We have a value where we get 240.1 megapascals. This is the contact pressure, otherwise known as the maximum contact stress. To calculate the contact area, we're going to use the second equation. Remember, A in this case is going to be the contact radius. So A is 0.908 times the force, 1,500 newtons, times delta, which is 1.2497 times 10 to the minus 5, 1 by megapascal, and then divided by 1 over radius 1, which was 6 millimeters, and then plus, but again, remember, radius 2 is negative because we have concave surfaces, so radius 1 minus 6.1 millimeters. And all of this gets raised to the 1/3 power. If you're wondering about the units, let's take a closer look. We have a Newton that is going to get multiplied by 1 over a megapascal, right? So a megapascal is a Newton per millimeter squared. So it's like we have a Newton per millimeter squared. And then at the bottom, we have millimeter. So 1 over millimeter. So the 2 newtons are going to cancel. And 1 of the top is going to cancel with 1 at the bottom. So when we type all of this in the calculator, whatever comes out is going to have units of millimeter. So if we plug this in the calculator, we get 1.725 millimeters. This is just the radius. And remember, when we have a sphere contacting, the area is going to be circular. So the area of a circle is pi times the radius squared. The radius is this A, right? So if we take this number, 1.725, we square it and then multiply times pi, we get that the area equals 9.35 millimeters squared. Now the last thing that we need to figure out is the maximum value of the subsurface shear stress. Remember, the important takeaway message whenever we have contact stresses is that the maximum value of the stress is usually below the surface. And specifically, the subsurface shear stress is going to take a value of 0.3 times your contact pressure. So if we want to calculate this value, we just take our maximum contact stress and we multiply times 0.3. So for this example, remember that the contact stress that we calculated was 240.1. We multiply this value times 0.3. And we get that the tau max is just megapascals. As always, if you pick up on any mistakes, please do let me know. Otherwise, we'll see you on the next one.